So I'm gonna continue with the explanation of the binder jetting. So binder jetting, the variables that are involved in the process itself are the binder saturation and the layer thickness. Although I haven't read anything about the type of binder that you use so far. Although it is a really fast and fairly cheap process to build 3D parts, the mechanical properties are really poor for this type of objects. So I think that it's fairly uh, you should consider the post-process of this part with the process with the manufacturer itself of this process. So the variables included in the post process are different depending on which post process you are talking about. And the three main post processes that I found are curing, infiltration, and sintering. In curing, the main variables are the binder properties, UV radiation, depending on if it is a binder that gets cured with heat or radiation, and temperature. For the infiltration, the variables are the atmospheric pressure in the furnace and the infiltration amount, the infiltrant amount. And for sintering, the temperature, time, and the pressure on the faces of the different faces of the object. Love these models, but they also submit this part to a post-process of infiltration with bronze to enhance the mechanical properties. So as in the different processes, we start with a CAD model. The powder that they use in this part is already metal. They work with titanium. Point depending on the part and the process, they are between 20 and 40%. They have between 20 and 40% density uh, before the post process. So what's going on there is that the first process is just the jetting jets binder in the powder to bind it together, and then they pass they apply a heat treatment to uh, dry the binder. So they normally fill in the space with aluminum peroxide, and they also put bronze in for this process and for capillarity phenomena. Once it's melted, it starts filling in or soaking, if you will, the the cavities we need within the object. So that's one of the post process. So the first research study is called Analysis of Ferroelectric Ceramic Fabricated by Binder Jetting Technology. And the specific scope of the study is try to obtain parts that can replace parts made with traditional or conventional manufacturing processes. So um, they build different parts using different combinations of variables for the binder and the temperature, and for the they don't use infiltration, they use sintering, and they use different times and temperatures in the sintering process, and they are trying to analyze and come up with a part that has the same qualities of other parts. So uh, this graph shows. Sorry, the question is that if bar titan oxide, I think it's called, that material can be used to fabricate parts with similar properties to those obtained through alternative manufacturing processes. And what they found is that at most they can obtain a part that is 22% dense, has a density of 22% if they use a 60% of binder in the injection. It's a 60% of the theoretical amount of binder that they can use. They can go over and up to 120%. So they detected using this method that the binder saturation, the powder size, and the sintering procedure have a significant impact in the final structure properties of the object, although they didn't they couldn't match the same properties published in other publications because they didn't use pressure in the process of sintering. So what they figured out at the end is that with that process and with that technology, they cannot match the properties of other objects made with other technologies. And the second research study is called Energy Consumption Model of Binder Jetting Additive Manufacturing Process. So this is study focuses on trying to identify a model that could predict the amount of energy used in making a 3D object. I think you may have seen this article. So basically what they do is that they identify the three main stages of making a solid part with binder jetting, which is uh, uh, setting a layer of powder, uh, jetting in the binder, and heating the binder so it can dry. And they also established that using the 3D model, they can establish the distances that the head of the machine has to move. And since it's a step motor, they established that the velocity of the moving parts in the machine are fairly stable, so they can uh, linearly predict the amount of energy. So in that graph, in the table of the left, they compare the simulation values against the real values, and the graph overlaps the two measurements, and they basically established that they can predict with a 95% of accuracy the amount of energy that is used in this type of process. My references.